Good evening. Okay, it's my great honor, okay, to uh, teach this subject, it's energy efficiency buildings. So I'm a Professor Vivian Loy. Yeah, you can call me Vivian. And so yeah, from our department. And this is the uh, first time we meet, I think in the coming weeks for my lecture sessions. So mainly include the first session, it will start at 6:35 to 8:05, and then we have around 20 minutes break. Then we will come back for tutorial session. Okay, tutorials and tutorial session. So this is the time arrangement for our lectures. So firstly, I think that's the design of this subject, the importance of this subject. That is because we can see with the rapid growth of urbanization and increasing concerns over climate change, especially the global warming and the frequent extreme weathers, the demand for sustainable development for the built environment has never been greater. And also our buildings account for, I think, the significant portion of global energy consumption and greenhouse gas emissions, especially like for Hong Kong. So we can see our building consumes around 90% electricity. Okay. So that's making energy efficiency in buildings a critical area for us to focus regarding the environmental and economic reasons. So energy efficient buildings are designed and operated to minimize the energy use while maintaining the improving occupant comfort and health and productivity. So this mentions we have to involve the integration of advanced technologies, innovative design from the design stage to construction stage and operation stage. So, and also it's very important, we also have to understand the relevant standards and policies and rating system that which will guide us to achieve, to guide our sustainable building practices. And let's see. So now not only our buildings account for the large portion of energy consumption, but also we can say due to the energy use, okay? Due to the high energy use, and there is adverse impact on our environment, including you can see in 2024, Hong Kong breaks 35 temperature records. So the monthly, the peak, the temperatures, and also last year we read new news, okay, from European countries. The heat waves caused death, and also so there's the frequent and long-lasting heat waves, not only causing the severe urban heat island effect, but causing the failure of the outdoor utilities and also even causing the deaths. So this is the arrangement. So because this is the second semester, I'm sure you all understand well about the teaching, okay, arrangement in Hong Kong, okay? And we can see, in fact, for this subject, we have two lectures, okay, including me and also one research assistant professor, Dr. Zhang Huan. Okay, And this is the contact hours, including so every day, for every lecture, I think 2 hours, 3 hours, 2 hours for lecture and 1 hour for tutorial sessions. And what about the assessment scheme? Okay, so there are 2 coursework assignment. The coursework including the seminar presentation and report and 1 mini project, which will be designed by Dr. Zhang. So you will learn write using Python to write a program to do the energy simulations. Okay, and the other one is very common. So it's a seminar presentation and a report. However, there's 1 3-hour closed book examination, okay, for this teaching subject. And for the arrangement, so, and today we will talk more about energy conversion, energy efficiency, and to also understand the end energy use and also for the building energy use patterns. And sure, it's important because the regulatory frameworks and standards will mandate, okay, our sustainable development design strategies. So it's also important to understand the regulatory framework and the standards. There are no in-class quiz. I think just a tutorial discussion. And then, so we understand, so the carbon peaking and carbon neutrality, and to understand the design strategies for energy efficiency building. And sure, so it's important to understand the building energy transition. And green building architecture, and also the passive design strategies, also active design strategies, and also how to implement the AI empowered so building energy management. So Dr. Zhou will mainly talk about the building energy management. So including you all together learn by using Python. Okay, so to work on the project and to understand the building energy management, and also AI-empowered building energy analytics and learning-based control, and also demand-side management. And so this is the arrangement of our this subject. So because some of you will try to connect with the other classmates to form a team for seminars and mini project. Okay, I think if you need, I think the numbers, seminar arrangement, I think 3 to 5 to form a team. And for mini project, if you really want to know now, I think I will ask, I will let Dr. Zhang design the mini project as early as possible for you, okay, to form a team. So for this project. And sure, anytime if you have any question, and you also have my office, my office is at ZS 850, and this is my email. So you are welcome to write to me, and also come to visit me for for any issues. Okay, I think you would like to talk to me, so including your study and your career development, you are welcome. So this is the teaching scheme, the teaching arrangement, and also assessment scheme. Do you have any question? Okay, if you don't have any question, then I think we will start our first lecture. Okay. I think I observed there are some students from the frontiers in carbon neutral cities. I think there is maybe 1/4 or 1/5 overlapped knowledge. Okay, actually, for that teaching subject and this subject. So now then we will start our lecture 1. So to understand more about energy and energy efficiency and energy end use. So firstly, we have to understand what is energy. What is energy? When we talk about energy efficiency buildings, should we talk about energy efficiency? So, but firstly, definitely, we have to know what is energy and what is the definition of energy efficiency. Okay, then first, what is energy? Okay, basically, so we think, oh, energy is just the ability to do work. Okay, so we do need energy to run, to walk,
One more scene.
to and we do need energy to do any work, including jogging, running, walking. Okay, but we will feel tired. That is because loss of our energy due to our action, movement. So therefore, we understand all such activities, movement will follow the law of conservation. Then in January, but for physics, we consider energy is a quantity that provides the capacity to perform work or provides heat. So energy comes in many forms, including the common forms of energy, the kinetic energy. So that is due to the motion. Okay, due to the motion. It's also called motion energy. Motion energy. So for example, so like the wind turbine. Okay, the wind farms. So the wind farms, in fact, is to capture the air movement, the motion energy of the air. So that is kinetic energy. So energy due to the motion. The common practice is we can see is the wind turbine. Okay, the air movement. So the air movement, there is a wind power energy. So due to the air movement. And this is the example for kinetic energy. Then we also understand potential energy. So potential energy is energy due to the position, merely due to the position. So is there any applications? The potential energy is hydropower. Hydropower, okay? Potential energy, I think the common, so is the hydropower, okay? The potential energy. So this is the energy due to position. And also internal energy and chemical energy. So chemical energy is energy due to the chemical composition. So look at here. Chemical energy is the energy stored in atoms and molecules. Okay? Then what's the difference between chemical energy and nuclear energy? Nuclear energy is the energy stored in an atom's nucleus. Okay? If you have the ability to release the energy, it's a nuclear energy. Okay? So we can say so for the combustion, the combustion of town gas, the combustion of fuels, the combustion of wood, all are releasing the chemical energy, the energy stored in the moleculars, okay, is the chemical energy. So the combustion of fuels is to release the chemical energy, okay, to release it, to convert it. The combustion is to convert it into thermal energy, the combustion process. And we also have electrical energy. However, in order for energy to change from one form to another, usually we consider the two transition processes is work and heat. So now we can see the definition of the forms of energy, including chemical energy, nuclear energy, mechanical energy, gravitational is the potential energy, and the motion kinetic energy, electrical energy, thermal energy, and even we can make use of sound energy and electromagnetic waves, the radiant energy. So now I would like to some of you to share the how to utilize the radiant energy. Would you like to share? What about the sun? The sun, the solar energy. The solar energy is the radiant energy, right? Okay. So, so we can see, in fact, not only the radiant energy from the sun, the solar energy, but there's a conversion. Always there is a conversion or radiant energy. Okay. And so to generally, I think because you all have a diverse background, so maybe we will go through those energy forms again, including thermal energy. So thermal energy is so we can understand is okay, there's a heat flow from high temperature to low temperature object. There's a heat flow. And the thermal energy, so the type of energy involved, so there is a give off heat or ended, being ended, heated. So this type of energy is thermal energy. And for thermal energy, for the electrical energy, so look at here, we can see it's simplified as the movement of charged particles. Okay, so electrical, even the lightning, okay, occurs. The battery can sense charged particles through a wire inner circuit. This is also can be considered as form of kinetic energy. And electrical energy is energy related to forces on electrically charged particles and the movement of these particles, also electrons. So we can see the battery, there is the flow of the electrons. And for the unit, okay, so usually electrical energy is usually sold by the kilowatt hour. Okay, so you pay your electricity bill, okay, based on the electricity, okay, electricity use. So aware that is the 1 kilowatt hour. Kilowatt is a rate. Kilowatt is a rate, and times hour is energy. So simply, yes, we should remember the unit. 1 joule is equal to watt times second. This is a unit of watt. This is a second, okay? then jiao. And also, there's one famous journal. The title is Jiao. Okay, it's very top journal. That and what is chemical energy? Is the energy stored in the bonds of chemical compounds. So the chemical energy can be released during a chemical reaction, often in the form of heat. And this is the nuclear energy. You know, because in Hong Kong, in China, Hong Kong and China, we have limited resources, energy resources, especially fuels, okay, fossil fuels. We have limited fossil fuels. You know, in China, Hong Kong, I think definitely all fossil fuels imported from other countries, regions. What about China? Okay, ask some of you to let us know. Like, what about petroleum? Do you have any concept? Do you think China can self supply enough or most imported?
Um, sorry, I didn't have.
Yeah, what are you? Want to share your on the news? You think
China has enough fuel in Heilongjiang province or Xinjiang province. They have
to you think we have plenty of fuels, fossil fuels?
no. S- as I'm concerned, there are also a lot of petrol source come from in the Africa or the
South America.
West Asia.
If you check the finger, I remember in China, like petroleum, 80% imported. Okay. So that's the reason now I think China, even Hong Kong, we have the ambitious plan to develop nuclear power plants. Okay. Nuclear power plants, because we don't have, I think, it's we relying on the imported fossil fuels. And then is mechanical energy. So this is the total of the potential of kinetic energy. Mechanical energy, so is the total of potential and kinetic energy. So potential energy is energy stored due to the position, okay? And so this is the mechanical energy. After understanding energy, we want to identify the energy sources and also their conversions. So because we are end users of energy, we want to know where are the energy sources. Then, and what are the energy conversions? So, like into electricity. So for our daily life. So firstly, let's see, I think the classification of energy sources. So for primary energy sources, so we consider there is renewable energy sources like from the sun, the radiant energy, solar energy, and wind power. So that's the motion energy due to air movement, and the biomass, bioenergy. Bioenergy is also, I think, it's the chemical energy stored in those biomass. Geothermal energy, this is the energy from the inner crust, inner core of Earth. So the geothermal energy, ocean energy. So for tidal wave energy, that's also the motion energy. Okay, the motion, the water, the ocean water, sea water movement. So that's ocean energy, and the hydropower is the potential energy, the potential energy of the potential energy. And and also in the coming weeks, maybe I also have the chance to introduce. We have the other renewable energy sources is the cold universe, because the universe is cold, and we understand cooling is difficult to achieve. So how to make use of the cold universe is also very interesting. And also hydropower, nuclear power, and also the conventional, the traditional fossil fuels. So for for traditional fossil fuels, so with the element of carbon, hydrogen, and oxygen. So so they include the coal, oil, natural gas, shale oil, tar sand, etc. They can be generally categorized as renewable energy sources and all non-renewable energy sources. And in fact, because we consider the carbon peaking and carbon neutrality, so we also understand and so the renewables and nuclear power, I think later we will discuss about the distribution of the energy sources for Hong Kong and for China. So like for an example is the energy, the radiant energy from the sun, okay? The radiant energy from the sun. So if you look at the feature of the hot sun, we understand it's super hot. Okay, so that is the reason it has its thermal radiation emission. So it has its specific solar radiation spectrum. Okay, this is from so if we want to say the utilization of solar radiation, we have to understand is the solar spectrum, because so for the solar spectrum, so the solar photons with the different photon energy, they can be utilized in for different purposes, and also by using different technologies. And also the coldness of universe. I think in the future, maybe I will also mention that. So for hydropower, maybe you think in Hong Kong. So when we on weekends, I like hiking. So we see there are so many water reservoirs. Okay, so for the dam, I think there is a level difference. There's also some plant to make use of those hydropower. However, from here we can see for renewable energy generation, so the first place is hydropower, is to make use of the and then comes the wind and the solar. So hydropower, we can see there is contributes to high share. We can see for Norway, almost I think it's 90 or one. I remember is 100%. 100% of energy is from hydropower. So for Norway. Oh, I think this is the Greenland. So we, Trump want to take it. So is this one? Is this the one? This is Iceland. I think this is Greenland. Okay, so we can see so almost all of their energy from hydropower. And also Canada, okay, we can see more than half of their energy, especially electricity, okay, from hydropower. And also this is Brazil. I think this is Brazil, and also Chile, okay, all with higher. And also, I think here around Switzerland, okay, because they have high snowy mountains. So for the hydropower, and so we can see this is in fact, is potential energy, is contributes, is the first contributor also for renewable energy generation. And so I think this is a beautiful video. This is a beautiful video telling the story about the hydropower. So from the snow, okay, snowflakes and snowy mountains, the snow melted, and then the water flow from high level to lower level. If we can capture, okay, this, make use of this potential energy, is can be used for hydropower generation. Okay. Sorry, I think I didn't share it. Okay, this is a beautiful story about hydropower. So, from the snowflakes to the snow melting, and if we make use of the potential position, potential energy. So this is the hydropower. So we can see hydropower powers so the northern northern European countries, and Canada, and also South America countries, etc. And basically, we can see this is the hydroelectric power system. So we can see this is the general, so the potential energy. Okay, potential energy can be measured by the, we can calculate based on the level differences, okay? Upper level and lower level water level, so the difference. And the potential energy will be converted into water movement, the airflow, okay? The airflow, the kinetic energy will be captured by the turbine, okay? then converted into mechanical rotating mechanical energy. If it's connected to a power generator, so it's the electricity will be generated. And then I think when anytime I talk about hydropower, I have to mention so the first inventor and who first helped us this world to harness the power from flow water is Nikola Tesla. Okay, Nikola Tesla. He is also the developer. He is the first person to develop the alternating current, AC power, and also induction. So also inductive charging. Okay, this is 100 years ago. His concept using wireless charging, and nowadays you are using it, the wireless charging, the first concept and also invented and introduced by Nikola Tesla. So he helped the first hydropower plant so in Nigeria fall. And then after understanding so the energy sources, then we know how from the energy sources to the energy end users. Okay, then it has to follow several energy conversions or transformations. So first, like for example, for a car motor, okay, for a car. So the combustion of fuel, like petroleum, so will release the chemical energy and convert it into kinetic energy of expanding gas, okay, the motor. While the combustion, the kinetic energy of expanding gas converted to the linear piston movement. Okay, then through several energy conversions, finally, the rotary movement will drive the wheels. Okay, will drive the wheels. So basically, so this the combustion of fuels to release the chemical energy and convert it into kinetic energy. Then kinetic energy converted to the linear piston movement. Then the rotary movement will drive the wheels of the car. Okay, this is then we can see there is energy transformations. And even for wind power, so when we mentioned the wind power, I mentioned is the motion energy or called kinetic energy. So this is by using the blade, okay, the turbine blades, the airfoiled air blades to capture the air movement, and then the captured wind power energy will be converted into a rotary. Okay, this is the blades, and the rotor converts the wind turbine to rotational mechanical power. Then, but we observe that the rotating, okay, the rotating speed is too low for power generation. Then we need to design the gearbox. So the gearbox, the function of gearbox is to convert, the rotating speed from low speed to high speed through the gearbox design. Okay, then finally it's connected to the power generator to convert the rotational mechanical power to electricity power. So therefore, we can see there are different components. The design of different components is to capture the energy, okay? and convert it to different forms of energy finally. So like for our electricity power generation is connected to the power generator. All the rotational mechanical power you see can be used to drive the car, for different purpose. And here, this one is for wind turbine for power generation. So there is the energy conversions from the blade. So if we have the chance to calculate the energy efficiency, of this wind turbine, then we have to follow, okay, how much wind kinetic energy can be captured. We have the Benz's law, okay, the maximum is 59.3% of the wind kinetic energy can be captured, okay, by the blades, okay, not all. And then there's mechanical components to rotational. There are losses. Finally, for generator, I think usually is around 20 to 40% of conversion efficiency of wind turbine. So therefore, we can see understanding energy conversions is very important. But we also have to understand thermal energy is unique because all other conversions, energies can be converted to thermal energy with 100% efficiency. Okay, so others to thermal energy, okay, is easily 100%. So we can, I think so. It's easy for us to understand. Okay, so when we scrub our hands, we feel okay. I think the kinetic energy, okay, into heat. But sure, if your hand is hot, it cannot help you move your hands, right? So we can see the energy conversion direction. All other forms of energy can be converted into thermal energy easily with 100% efficiency. But thermal energy, if you plan to convert thermal energy to other forms of energy, there is efficiency. Also, it cannot be achieved easily. You need to design machine or equipment or devices or heat engines. Okay? So all other forms of energy can be converted into thermal energy easily. So, and also efficiency almost 100%. But for thermal energy, it cannot be easily converted into other forms of energy. Okay? So thermal energy is very unique. Then after understanding energy, what is energy? And energy we understand. So the available energy sources for us, and we know for the energy end user. So for that, there's a different. It will follow different energy transformation processes. Then we want to know all such energy conversions have to comply with thermodynamic laws. So the zeroth law, the first law, the second law, and the third law of thermodynamics. So then we understand all energy conversions has to comply with the thermodynamic laws, especially the first law and the second law. And also then we will together know more about energy efficiency because they are all directed to building energy efficiency. Because when we talk about building energy efficiency, we have to know what is energy efficiency, where energy efficiency for energy conversions, okay? Energy conversions. Because look at there, thermal energy is easy to achieve, but thermal energy cannot be converted to other forms of energy. So we need design, so the engines, okay? And so then all our energy conversions have to comply with satisfy the first law of thermodynamics and the second law of thermodynamics. And first law of thermodynamics let us know the energy conservation. Energy cannot be conserved or destroyed. It can be only converted from one form to the other. This is first law, is energy conservation. Energy cannot be created or destroyed. It can be only transformed from one form to the other. Second law let us know the direction. For example, kinetic energy and can be converted to heat, but heat cannot be converted to kinetic energy. That means all energy conversions, energy processes, it takes place in a certain direction, and all energy has their value and quality. Okay, for example, if for the water, the same water holding the heat, so with high temperature and low temperature, they have different energy values. Okay, different temperatures, and also I think I need to, because I think it's screen. Okay, then maybe I think maybe some students don't have the background of so cannot remember, or so energy thermodynamic law, but I think it's very important. So maybe we together, okay, to understand the first law and the second law, understand all our energy conversion processes have to satisfy not only the first law but the second law. Okay, then we following it. get the information. So when we talk about energy efficiency, you will think where's the losses. Usually all the losses becomes heat, waste heat. Okay, all the losses usually are the waste heat. And so let's see the second law. Maybe I skip second law, so we will know more that together. I think due to time, so we don't have time to. Then, so the second law is telling us the directions. So the conversion of the examples, including the conversion of thermal energy, the thermal energy into electricity. That's for power plant. Okay, I think later we have examples, okay, together to do the calculation and understand for a power plant, okay, what's the energy conversions and what their energy efficiency? What are the strategies to improve their energy efficiency, okay, to uplift their efficiency? And also the other common examples for us is for air conditioning, Okay, then we have the discussion question for us to understand how to, for our engineering practice, how to improve, uplift the performance efficiency, the efficiency. Then I think we don't have enough time to watch the second video regarding the second law, and you get the link, and you can watch it by yourself. Then now we know about energy conversions. We also know all the conversion processes have to satisfy the first law and the second law of basic laws of engineering thermodynamics. Then we want to know what is efficiency. What is efficiency? And because we can see even for the light bulb, okay, there is input energy like 1 joule electricity input. But we observed that only 25%, 25 joule, okay, converted into light through the bulb. Then we observe the losses. Okay, the losses is the heat, wasted heat into our environment. So then what's the definition? The definition is very simple. Energy efficiency, the formula is very simple. Is energy output. Is the output. The desired output, the ratio of desired output to the energy input. This is the definition of energy efficiency. It's very simple. Then we have the case, okay, for this light bulb. What is energy efficiency? Okay, so for example, if the input energy is the electricity is 300 joule, and we observe that the useful energy output of light, okay, is 30 joule, then the efficiency is 10%. Is 10%. Okay, is 10%. Then we understand. So previously, the light bulbs really that's also one of the reasons why we talk about so the energy efficiency lighting fixtures. Okay, so because previously the light bulbs, the efficiency is really lower than 10%. Okay, the conversion, and this is for the lighting fixtures, lighting bulbs. So what about so electricity consumption for other like the motors, the electric motors for lift, for escalators, for other okay. So I think that's mainly for our buildings is the lift and escalators. So its efficiency can be very high, But we got another question. This is the design for full load is 100%. What about because our energy systems operate at part load during operation is another story. Okay, these are usually the design condition. So for the operation mode, it will be another story. Anyway, I think for the regarding the device, the equipment, the efficiency already very high. Okay, already very high. But as an engineer, so during the operation stage, okay, how to keep them, okay, operate efficiently. So we also have to consider like the different energy saving strategy. So then this is the regarding the second law of thermodynamics is all other forms of energy can be converted to thermal energy easily, but if it's the thermal energy can converted to power, that is for power plant. Okay, this is the concept for power plant. Okay, for power plant is the combustion of fuels, the combustion of fuels to release the stored chemical energy into thermal energy through the power plants or the forward heat engine. We plan to convert it. Okay, so this is the work. What is we expected? This is the output. Okay, expected output, and this is the input. Okay, this is the input. This is output. That's for power plant. Then we are usually we consider the theoretical forward heat engine as a Carnot engine. Okay, Carnot engine. So then the Carnot cycle describes the maximum highest conversion efficiency from thermal energy into power. Okay, this is the formula. Okay, the Carnot cycle formula. So the Carnot cycle formula let us know, okay, the maximum theoretical thermal conversion efficiency from thermal energy into power or electricity work. Okay, and then from this equation, so we can get first there is a theoretical limit. Carnot efficiency is the theoretical limit. This is the highest. So the theoretical limit is only function of two temperatures. One is the source high temperature. One is the low temperature for the cold sink. Only related to the two temperatures. Now you understand. If then we understand if the high temperature higher, okay, higher source temperature and lower cold sink temperature means higher efficiency. Okay, so that's the reason we don't use the boiling water for power generation. Okay, because the temperature is too low to be utilized. So, and then we can get lots of information from the key concepts for power plants. We understand. So with the two given temperature, source, and a sink, we know the maximum theoretical efficiency, and we understand how the efficiency will change with the high temperature and the low temperature. Sure, this is the ideal theoretical heat engines. In reality, this heat engine is more complicated. Okay. Then I get an example. I would like you to calculate, to basically understand, help our power plant to do the calculation. Before calculation, I think it's also good again to understand where is our electricity from. Okay, so through watching this video, we understand how a power plant works, how it can convert the thermal energy, okay, into electricity.
steam turbines lie at the heart of these power plants. They light efficiency.
Okay, basically, we can see for power plant is through the combustion of fuels to produce high temperature, high pressure steam. Okay, then the steam enters the steam turbines. This is we understand the airfoil blades design to better convert the energy held by the high temperature, high pressure steam into rotational mechanical energy. And here is a power generator, okay, connected to power generator for power generation. So this is the basic how for a steam turbine works and for power plant. And then we understand. So now I would like see this is okay. I ask some of you. Let me know. So what is this? What is this? The released gas. What is this? Would you like to let us know what is that? Chimney. Okay, this is a chimney to release the combustion gas. Okay. Okay, it's the products were combustion. Okay, and then what about this? Cooling towers to reject the heat, because we remember if here is the work output, okay, and then this is the heat which will be released to our environment, is unuseful waste heat. This is unuseful waste heat. Okay, this is the input. This is the useful output. This is unuseful waste heat. Now, so I got these fingers because we understand the steam turbine usually can hold serve the fluid around temperature 500 degrees Celsius to 600 degrees Celsius. Then we consider it as 550 degrees Celsius. And we consider the cold sink. The sink temperature is 40 degrees Celsius. Would you like to help me calculate the theoretical maximum efficiency? Okay, do you want to calculate by yourself? Okay, if we can calculate together, it's also okay. Okay, so this is energy conversion of the power plant. So we understand if for the maximum, okay, sorry, I forgot, is for the theoretical, okay, theoretical maximum thermal efficiency is the Carnot, is the low temperature, and this is a sink. This is for the source. This is means subscript is high temperature. This is the low temperature. Okay, then for this one is 40 degree. Okay, is the condensation temperature, and then the high temperature. So anyone, would you like to calculate and let me know the efficiency? What's the result? 62? 62. Thank you, 62. Okay, the maximum highest thermal efficiency is 32%. Then we understand 38. But you know, most power plant, I think this figure is around 40, okay? With different strategy, reheat strategy different, maybe you can achieve 50, 60. Then 38% of energy will become waste heat. Waste heat, okay? waste heat. So if the rated power plant is 100 megawatt plant, that means this amount of heat has to be rejected to our environment through the chimney. Okay, the cooling towers. Then we understand, okay, basically, if the high temperature, okay, for this is 32 megawatt, okay, waste heat. And what we expect is higher temperature, okay? And condensation temperature is the cold sink, is lower, is the better, okay? And sure, so in engineering practice, they have different strategies, okay, to improve the efficiency. But generally, the conversion efficiency is not that high. Then we look at the air conditioning. So that's for the, because heat is always transferred from high temperature to low temperature. If from low temperature to high temperature is called refrigeration technology. Okay, refrigeration technology is like our home. This is the air conditioner, like the indoor room. Okay, it's the evaporator. So due to the evaporation of the refrigerants, heat will be absorbed by the evaporator. And then there is a compressor consumes electricity. However, considering energy conservation, then more heat will be discharged to our outdoor environment. Okay. Then we have for the second session, we also have an example to do the calculation. So if, for example, I think it's 2 kilowatt hour cooling, and if it's 1 kilowatt electricity consumption, then that means we have to discharge 3 kilowatt hour the rated waste heat into our environment. So that's the reason urban heat, one reason for urban heat island effect. For built environment, we provide cooling, but we discharge more heat into our environment. So this is the working principle of refrigeration. So for air conditioning. So then, and for the refrigeration, if it's simply reversed Carnot cycle, then it's also related to their temperatures. So this is the cooling temperature. This is the condensation temperature. So if for cooling purpose, so we can say if we want to so to examine the energy efficiency of the air conditioner or chiller plants, we are using COP, coefficient of performance. Okay, coefficient of performance. So directly, it also can be seen is if for the theoretical coefficient of performance is also function of the temperatures. Okay, the cooling temperature and also the condensation temperature. So maybe would you like to share? So if the cooling temperature higher, the higher COP, or lower, the higher COP?
Higher COP.
You mean the cooling temperature higher is a higher COP?
Higher COP is the better performance.
Yes. Okay, thank you. So when you talk about the radiant cooling, ceiling cooling technology, radiant cooling technology. Okay, so conventional one, the chilled water supply is 7 degrees Celsius, right? is 7 degrees Celsius. But for the radiant cooling technology, the supply can be 22 or 12 or higher. So that means this temperature gets higher. Okay, if the cooling temperature gets higher, what about the COP? Is also higher. That means consumes less electricity. Okay, then is mentioned means, okay, this is the cooling temperature. Okay, if it's higher, then the COP is also higher. That means energy efficiency technology. Okay, sometimes we will see for radiant cooling, ceiling cooling. Okay, radiant cooling technology, we can using higher chilled water temperatures. That is because we can increase the COP of the plant, which means consumes less electricity. So this technology, we can call it energy efficiency technology. Sure, another example is for the heat rejection, okay? The outside temperature. So for the selection of outdoor units, what's your plan? So you want to choose the outdoor units better preferred in a ventilated place or the place with the dead air circulation. Which one is better? So your home air conditioner outdoor units, the surrounding temperature will also affect the performance of your air conditioner. So that means if you are choosing for the heat rejection environment is a lower temperature environment with ventilated instead of okay with the dead air. So if it's lower, that means also higher COP. Then it can also help you reduce electricity consumption, save electricity bill. Even as engineer, I think the location of the intake, fresh air intake LOFA, and even for the heat rejection unit, ventilated space is very important. Otherwise, heat will accumulate there. So maybe surrounding, say, over 40, 50 degrees Celsius, it will largely reduce the performance of your air conditioner or your chiller plant. So we can say, if that's the reason why I always want, before we talk about technology, I also want you to understand the fundamental knowledge, because this knowledge can help you to identify if a technology is energy efficiency technology or not. Okay, you can using our knowledge to judge. So this is we can see we can implement the strategies, including increasing the temperature. Like one application is the radiant, the radiant ceiling cooling technologies, and even so for the heat rejection environment, choosing a lower temperature, etc. So in fact, there's many power generation technologies, not only for the nuclear and combustion of fossil fuels. So we also have like solar energy, wind power, hydropower, etc. The combustion of biomass also release the chemical energy stored in the biomass and geothermal energy. So then I also want to talk about so when we talk about power generation, we just do the calculation about here is about for power generation, the efficiency, and for air conditioning, for refrigeration, and also the efficiency. Okay, efficiency is here. And then I would also like to ask you about the efficiency of solar cell. So we see there's many different types of methods for power generation. So one is using the solar energy. So then what is the working principle? This is the radiant energy from the sun. Okay, the cell calculation is simple. So because we want to get I think it's not correct. Is the output or the input energy, okay? The received solar energy and the input. So this is the working principle. This is the solar light, solar photons, okay? It can strike off the electrons, and also the solar cell, the materials can create the p-n junction, and then the all electrons collected by the grid, metal grid, and we connected with the external circuit. There is electron flow, then there is a current. Then now I would like to ask you about your understanding. We talk a lot about the power plant, the efficiency. I think it's usually around 30 to 60% for different power plants. Okay, then we reject more energy as waste heat into our environment. And what about solar cell? What do you think? Efficiency is very high or low? What's your option? Choice.
I think I will choose the option D for the solar.
Okay, option D. You believe solar energy conversion is higher than the conventional power plant, 70 to 80%. What about you? C. C. Oh, 30 to 40%. Okay, similar. Okay, I think you know the answer. Okay, what about you?
A or B, based on your type.
Okay, A or B? A so low. Okay, that's 10 or 20 years ago, the efficiency. Okay, I think for most types, but most common types of solar cell in commercial market, yeah, it's the answer is B. Most common types of solar cells for monocrystalline silicon solar cell, amorphous silicon solar cell, and thin-film solar cell is around 10 something or 20 something, okay, percent. Then we got the idea. It's really difficult, okay, so electricity. So the conversion efficiency is low, not that high, okay? It's low, even for solar cell technology, solar photovoltaic technology. Okay. It also has its limit. Okay, the limit is around 32, 33. That's the maximum we cannot achieve. Okay, so that's the. Then we also, but we also understand this efficiency will also decrease with the cell temperature. Okay, if the solar cell, so we can see where's the other energy. So only 30%, only 20%, 15 to 20% solar energy can be converted into electric power. What about the rest? Okay, becomes heat. Okay, waste heat. So heated our solar cell to 70 degrees. Okay, so under sunshine, the solar cell temperature will increase, roll up to 70 degrees Celsius because all other energy. So as I mentioned, energy efficiency, where's the rest? Waste heat. Okay. So then when we talk about improve the efficiency, increase the efficiency, that also means less waste heat into our environment. Then we talk about energy efficiency. We will also want to know about their emissions. Okay, Sure, there are emissions like different types of coals with carbon capture or not. They also have different greenhouse gas emissions. Sure, that's for the conventional. So fossil fuels have higher say greenhouse gas emissions. It doesn't mean we don't have emissions for renewable energy. Because for biomass, for PV solar cell, for thermal solar PV energy, geothermal energy, we still need to, we also consume energy to produce, okay, to manufacture, to produce the solar cell for the system installation, etc. That doesn't mean totally no emissions, okay, for renewable energy generation, electricity generation. So here is roughly a finger telling us the emissions for different types of electricity generation technologies. Then I think we will leave it for discussion later. We will quickly go to. So after understanding energy source, energy conversions, and knowing more about energy efficiency and also energy conversion has to satisfy with the first law and the second law. Then is we understand as energy end users, okay, the demand side. We want to know more about energy and use. Okay, first finger, that's for China. So for China, we can say, sure, in 2035, there is a peak. Okay, carbon peaking. Hong Kong, we have experienced our carbon peaking several years ago already. And China, we expect, okay, this is a critical year. So, and we can see the energy consumption mainly by the energy intensive industries. So due to the fast economic development, sure, even the EI industries consumes more energy. Okay, and sure. So in the future, other industry and also residential, we can see that still experience increasing energy consumption. That's due to, so we try to provide comfort, okay, and safe built environment. So if you read the news, we talk about the heating in countryside in Hebei province. I don't know much about that story. I think maybe I would like to invite some of you to let us know, because I read the news about people in countryside, it's very cold for them, but they don't have heating. I don't understand, because the government, the policy prevent from the combustion of coal and wood. Is it that story? Do you want to tell more about the heating and the current? I think there's many news about that for Hebei province. The people in countryside experience extreme cold, but heating is too expensive for them. It's due to, I think, maybe that's due to elevate the air pollution problem of Beijing. Then they pervade the people around. No direct combustion of coal or wood or something, I think. So that's the story. So then when we look at the total energy demand, okay, and this is the supply side. Sure, there's a declining, share by the coal, and natural increasing trend for natural gas, and also nuclear power. So, and also we largely develop wind power and solar PV technology. So we can see in the future, we have more, the energy is share from natural gas and nuclear power, and also wind and solar PV. That's for China. And this is the that's for China. What about Hong Kong? So Hong Kong, and maybe I leave it to the tutorial session, and is the energy end use data set, okay, released by the EMSD of Hong Kong. So talk more about, but this is mainly energy end use from the production to the end user. So let's quickly have a look at the finger. And so this is the total energy consumption in Hong Kong. Okay, the mainly 40%, 60% of total energy consumption by fuel, okay, is electricity. So electricity for commercial buildings, for residential buildings, 27%. Because residential buildings, we still even for the heater, okay, for the shower is still the combustion of town gas. So we can see in the and for residential buildings also 14% by fuel is for town gas and LPG. And also for oil and coal products, that's mainly for transport. Okay, I think Hong Kong is still on the road towards electrification. Okay, electrification of for transport sector. Not like China. I think like in Shanghai, most cars are electric vehicles. Okay, so it's now the road is very clean. Okay, so and so by sector, we can see our commercial sector consumes 45% of energy, and the residential, I say, comes the second. Okay, consumes around 23% of energy, and it's also very the transport sector consumes the second. Okay, that's mainly consumes oil, coal products, and less electrified. So I think only for the MTR. Okay. So then for the by end use, so we can see, okay, the largest sector, okay, the end user is air conditioning. So we can see here is air conditioning and also refrigeration. Then we just talk about how to improve the efficiency of the cold hour performance of air conditioning and refrigeration. Okay, so it comes around is the first. Okay, the first energy user is air conditioning and refrigeration. Sure, the second is for cooking. And also lighting. Lighting is also 6%. And our office equipment and industrial process equipment and vertical transport. Okay, now because for high-rise buildings, the vertical transport, that's mainly the motor. Okay, the motor. So we talk about the efficiency of a motor. And the goods vehicles, the bus, the taxi, the marine, and others. And even for electricity, the end users for electricity, also the first is and together air conditioning and refrigeration together over one third. and the lighting is around 10%. So as I mentioned, so most lighting fixtures with low efficiency, okay? So we are talking about LED, etc., with higher energy efficiency is also very meaningful towards energy efficiency. And also cooking, hot water supply, so the vertical transport, etc. So now we understand if we plan to achieve energy efficiency buildings for those energy end users, okay, we know where is our focus. So for air conditioning, for lighting, for vertical transport, for etc. Then we can see renewable energy shares, I think, very tiny. So they even didn't share with us. I think the nuclear renewables, they are included, and together with the nuclear power, I think less 1% of contribution to the energy sector. So in Hong Kong, and for renewable energy, that's mainly from waste to energy, so the biomass energy, and then comes the solar energy and the biodiesel, and also wind power and hydropower. So that's for the data. And basically, we see so Hong Kong, our buildings account for is as the energy electricity end users, so account for 90%. 90%. Okay, 90% of electricity are consumed by our buildings. So the types of energy consumed in our buildings, including electricity, town gas. Okay, town gas. So this is the composition of town gas for Hong Kong. So we can see there have the methane and the hydrogen. Okay, so we can see for our town gas, we are consuming hydrogen. Okay, consuming a hydrogen. That's for the composition of town gas we are using. If your cooking set is using town gas, okay, so half. Although its energy value is relatively smaller than the methane, but it's still okay. So that's also because of it. This is the color of a cooking set. Is the blue is due to we have the hydrogen, and sure, we also have oil or petroleum or coal, other possible fuels, which are also using for heating, cooking, hot water supplies, and even we also need water for cooking, heating, hot water supply, etc. And lastly, I would like to mention, although we talk about the energy consumption in buildings, however, due to the penetration of renewable energy and the changing patterns of our the end users, okay, the change of the patterns of energy and also the high penetration of renewables. So we're talking about the flexibility and the resilience of our energy system. So now energy flexibility and energy resilience. It's very, very hot research topics. They are very hot research topics related energy flexibility. That is for smart grid and the high penetration of renewables, and also the changing mode of the end users, energy end users. And so there's we talk about energy flexibility, and then thermal storage is also very important, because we can see there's the electricity demand, there's large fluctuation, and we need the energy flexibility balance, and we need also storage technology and flexible energy generation, and also other energy storage technologies. So for energy storage, we have several different technologies. So for the conventional one, we understand is using battery, okay? Battery to store the electricity, I think it's in thermal energy, okay? In chemical energy. chemical energy. And also, if you are using the ice, you don't need to take a photo. I think I upload this version because I'm still revising my PPT before I coming into this room. Okay, I have uploaded the newest one. I think at 5:40. Okay, 5:40. You don't need to take a photo. I have replaced this this latest version there. So there are many different types of energy storage technologies. So the common one, we are using batteries, but we are also familiar with the thermal energy storage like ice thermal storage technology. If you are in Hong Kong, we talk about district cooling. We are also using ice. So we are using ice to store the cooling, okay? The cooling. We produce ice at night in the evening and release the cooling during daytime. It can not only shift the peak of electricity, but also it can reduce the installation capacity, okay, for your equipment and the system. And also, I'm also working on using the to balance the grid. Okay, I also can be the electricity can be used for hydrogen production. That's also one of my research. So I think about the wind turbine. So if there's for the actual power can be used for hydrogen production. This is also called green hydrogen. Green hydrogen. And sure, what's the common storage technology for power plants? In fact, is pumped hydrogen. So they are using the waste electricity to pump water from a lower reservoir to an upper reservoir. Okay, during daytime. So then using the potential energy to produce, to generate electricity. This is also very common, okay? Using the pumped hydropower technology to balance the load, okay? Because we can see the demand is really fluctuate, okay? Really fluctuate. So there's a lot for us to rethink. In fact, not only as energy end users, the demand side, but we also have to look at the supply side and also understanding the energy conversions and the technologies, and be careful of their efficiencies. So that's the reason for the first lecture. So for the energy regulatory frameworks and standards, maybe we also leave it to later. So basically, we have to understand the government has established a regulatory framework and a set of standards to guide the design, construction, and operation of our buildings. So all are under the Buildings Energy Efficiency Ordinance. It's ordinance, okay? So it mandates the compliance with the Building Energy Code and Energy Audit Code. I think maybe I'll leave it to the last lecture, but now just a quick briefing. So it also requires us to retrofit new building retrofits to meet the minimum energy efficiency standards for our air conditioning, lighting, electrical appliances, lift, escalator system, because they are the main energy users, electricity users, and even energy audits, building energy code, and energy audit code. That is under the Buildings Energy Efficiency Ordinance. Then for it's not mandatory regulations and guidelines that's including for Hong Kong Green Building Council, and it's BEAM Plus. Okay, let us it's the green building assessment tool for existing building, new buildings, for different types of buildings. And sure, our government also has the government initiatives and incentives, okay, to promote energy efficiency. Okay, that's for this one. So, and this is a brief summary of those policies and the energy codes in Hong Kong. Okay, for air conditioning, for lighting, for lift escalator, for electrical installations, and for energy audit, for OTTV, over thermal transfer value, and for freshwater cooling towers, for labeling schemes, for mandatory labeling schemes, etc. Okay, sorry for delay. So come back in 10 minutes. Okay, we reduce to 10 minutes. Then we come back for in-class discussion. Thank you. So if hard for you to understand some of the calculations or concept, you can approach me. Oh, it's great. I see some old faces. Oh, okay, nice to meet you. Okay, because this is the first week, I think some of you still hesitating to take this subject or not, right? And drop week. Okay, so for the closed book examination, I think I usually design 40 multiple choice questions. So each one carries 1.5 marks. Okay, so if you ask the question, I think it's just most from the PPT. But you need to understand. If you don't understand, sometimes you still cannot get the correct answer. So I just did this. If some students will have the experience, I think I designed the multiple choice question. I have designed like understanding solar spectrum. Okay, its wavelength and the peak. Now later I will talk more about solar energy. Okay, the peak energy, the peak intensity is visible light. Is visible light. Okay, visible light. This is near infrared light. This is UV light. So this is the peak. Is for highest energy intensity is visible light. And I remember I also before I designed the question regarding the efficiency of a light bulb, okay? And also the efficiency, okay? I remember I designed one question about power plant, okay? I give you the two temperatures, calculate the maximum thermal efficiency. So here, if for the students without engineering background, so understand this is called absolute temperature. Okay, using unit is Kelvin degree. Because why there is a Kelvin degree? Because for engineering thermodynamics, we think all object is absolute temperature is larger than 0 Kelvin. If it's 0, it means atoms will stop. No radiation doesn't exist. So for engineering thermodynamics, for all the calculation, we are using absolute temperature. So this is the common one in our daily life. We are using degrees Celsius. This is the Kelvin scale. It's a different scale for energy thermodynamics. That's merely the third law of thermodynamics. I remember I designed this one as well. And so we can see it's also easy for me to design a question. So you understanding this based on this equation, like so the strategies to improve to increase the efficiency. Okay, consume less electricity for air conditioning system. Okay, I give you a technology. I let you judge if it's energy saving or not. So that's the for the multiple choice question. Before I will design two questions, I think short questions, just like similar, let you do a little bit analysis. No one will fail the subject usually, okay? Oh, I cannot say that because if you are absent, okay, you fail the subject. According to my memory, okay, no one failed. No one will fail. But if you want to, anyway, for my, I think for my subject, usually the average is B and B plus. Okay, some professors are very strict because we just there's a sub. All lectures will report their grading results for each subject. Some professors' average is B minus or C plus. And some professors are about B. I think for my one is between B and B plus. I think pushing B plus for my teaching subject. I think even yes. And if you really worry about maybe there's a chance for you to fail the subject, you can approach me before the examination. Before, okay? I can offer you a free private tutorial, okay? Tutorial session, but not after the exam, okay? Before the exam. So if you are worried about failing the subject, fail the subject, okay? Okay, then is the session, I think, for free in-class discussion. I think this is the assignment for, this is also your assignment to read the Hong Kong energy and use data, okay, to know more about energy end users. So I think I have you have the documents, okay? So then you got information about about the energy flow diagram, okay? Even energy flow diagram, and the overview of so in the past few years. So we can see the energy end use per capita also decreasing, and electricity consumption per capita is also decreasing, etc. You can got all the information, and also in the previous report, we also understand the pattern, the energy use patterns. Also, there are changes of energy use energy use patterns. So like for data center, energy consumption for data center, for transportation are increasing. Okay, maybe I give you 5 to 10 minutes, have a quickly, okay, you quickly read this report and find the the useful information for you. Okay, okay, 10 minutes. So we can also see this is the mandatory energy efficiency labeling scheme. We mentioned, but we didn't mention the details. So this you can reading the labels. Okay. So we can got all the information we got. Okay. So I think it's important for us to understand as energy end users. Okay. So the energy use data is also very important for us to understand where we are and then um, how to achieve low energy buildings. And first, second discussion question is about, I think I'll give you 3 minutes, okay, for the second question. Then I will ask 2 or 3 of you to share your insights, okay? How the combustion of fossil fuels contributes to carbon emission. What's the reason? And also, how the carbon dioxide levels in the atmosphere will cause global warming. Okay, the second question. Okay, so please get your solution, and I will ask 2 of you to share your insights and your views. Okay, time. Any volunteer to share? It's very simple, right? The combustion of fossil fuels will release carbon emissions. Why? Do you want to share your views? Why? We did. Okay, what about you? Do you want to share? Okay, come and teach us. The first, how the combustion of fossil fuels. So so why? So we always talk about the combustion of fossil fuels. Power plants will release carbon dioxide. What's the reason?
As we know, the fossil fuel, they all come from a million years ago, organic or something else, and it contain the element of carbon. Then the carbon, then
Okay, so for fossil fuels.
yes, for fossil fuel, it contain carbon. Yes. Other like hydrogen, sometimes it conclude I don't know how to say S 硫. Yes. So when we use this fossil fuel to for energy generation or something else, it will react with oxygen and it yes provide the GHG as we know is greenhouse gases. Mostly we talk about CO2. So this is playing the question 2, I guess. For question 3, as we only question 2. Okay. I think that's all.
Okay, thank you. Okay, I ask some of you think you understand? Huh? Now you think you understand? Why? What about you? Do you think you understand? Okay. So the biomass and the fossil fuels, I think they're chemical, they're organic chemical compounds. Okay, it contains carbon, the element carbon, hydrogen, and oxygen. Okay, so and sugar and also other elements as well. So the combustion of those fuels. Okay, this is the combustion equation. So the purpose is through the combustion to achieve heat, okay, the thermal energy for use. And however, there's byproducts of the gas emissions, okay, the byproducts of the greenhouse gases. And the greenhouse gases in the atmosphere, not in this room, okay? The concentration level of carbon dioxide in the atmosphere, so here is, so carbon dioxide concentration levels in the atmosphere, okay? Not in this room. So for this room, so sure, we also need the ventilation system to remove the carbon dioxide generated by us. We people also generate, when we are breathing, we also generate carbon dioxide, okay? And then later, maybe we also understand, okay, this one, so the global warming and the energy balance of the third question. So so following the first law, there's energy conservation. So if this is the Earth, Okay, this is the Earth. This is the sun. Okay, I think as we remember is Kelvin degree, say 5,000 degrees Celsius, and our space is cold. Okay, our space is cold. So that's if it's the moon. If it's the moon during daytime, 24 hours for day and for 24 days for day, 24 days for night. Okay. So if we on the moon, due to very thick atmosphere, if during the daytime, the moon, the surface temperature, I think it's maybe will be over 100 degrees Celsius. Okay. And at night, when there's so for the shading side, maybe it's lower than 100 degrees Celsius. Okay, that's due to the thin atmosphere. Okay, on the moon. So, what about the Earth? We have the atmosphere. Atmosphere is a thermal regulator. The atmosphere. Atmosphere is a thermal regulator of the temperature of the Earth, Okay, so which means, okay, the solar energy is the main energy source. And also the Earth, there is we radiate heat. Okay, we radiate, there's radiant heat energy transferred from Earth into the cold universe as well. If this one in and out, if it's equal, that means our Earth's temperature is constant. Okay, the Earth's temperature is constant. Energy conservation, so how much received and leaving is same. Then there's energy balance. Now, because the atmosphere, the carbon dioxide concentration level increase, and water vapor and carbon dioxide are the two main greenhouse gases, water vapor and carbon dioxide. So they will absorb, will trap the heat release into the space. Usually around 80% of radiant energy from the Earth will be trapped by the atmosphere with the increasing concentration levels, carbon dioxide and water vapor. So now yin is larger than the living energy. Then, so we have the equation, I think we all remember. So this is year 3. So for local students, year 3, so physics you have learned, because my younger son is Form 3, now is preparing his examination. I also is talking about heat capacity. Okay, then causing the temperature increase. So this is global warming. Okay, this is the reason. And later, maybe if I have a chance, I will let you know how the carbon dioxide and water vapor in the atmosphere will trap the heat, leaving the Earth. Usually around 80% will be trapped, okay? But it's good because we have an atmosphere is a thermal regulator, that the temperature variation during daytime, nighttime not that much. So we have some experience. If it's a clear night in the early morning, you feel the temperature drop is severe, right? Large temperature drop. But for cloudy day, so the temperature variation during daytime and nighttime is small. So this is the third question. For the last question is the air conditioner. So I think I have let you know let you know. So I think we find the question. Here. So this is an air conditioner. I think this is like, for example, this is the wall, okay? This is indoor environment. This is indoor environment. This is outdoor, okay? So the working principle of air conditioner is indoor is evaporator. The refrigerants will experience phase change from liquid to vapor, vaporization. We know during the phase change period, it can absorb large amount of heat from its surrounding, okay? So due to phase change of refrigerant from liquid to vapor, so it can provide cooling. So for the question, if it's provide cooling, so when you home, you plan to buy for your apartment the air conditioner, you will check the cooling capacity. Okay, this is the cooling capacity. And then I let you know the COP is 2. So the definition of COP is always expected. What you expected, what's your desired, okay, output. This is expected output over input. So for air conditioning, for home air conditioning, so simple, because expected is the cooling, okay? Then it's 2. If the COP is 2 for the tutorial session, then that means input energy is 1 kilowatt. That means is the noise from, okay, the compressor. The compressor is 1 kilowatt. So then we see its cooling effect is the surrounding absorbing heat, receive heat, okay? For the evaporator is receive heat, then your room feel cooling because heat is removed, then provide cooling. Then based on the first law, energy conservation, for the air conditioner, receive 2 kilowatt from its surrounding. Okay, input electricity 1 kilowatt, then energy conservation. So the rejection to out environment is 3 kilowatt. Okay. So the results is 3 kilowatt heat will be rejected to your outdoor environment. That's the one reason contributor to urban heat island. So our air conditioning, so always you should remember the definition equation, even efficiency and coefficient of performance is all expected output. What's your design? What's your expect over the input? So for air conditioner, we consume electricity. And then maybe you are curious about why the efficiency, the COP can be larger than 1. That is because this is high quality energy, electricity. This is thermal energy, heat. They are not equivalent, okay? They're not equivalent. So the COP for central chiller plant maybe is 5, 6, okay? Don't question about that because the input is electricity. Electricity is high quality energy, okay? Highest quality energy. It's different. So the COP, that's the reason COP is larger than 1, okay? But for thermal energy into electricity, the efficiency usually is around 40, 50, okay? That's for the tutorial discussion. So that is chance, okay? So they can be examined in for the multiple choice question. I think it's very simple. What I try this design question, simple question for you is I let you understand. Cooling is not free. In fact, when we provide cooling, we generate heat. We generate heat. And yeah, we release heat to our environment. Okay. I see I have let me see. I have if I have yeah, this is almost this is okay. This I think at the end of our lecture. Okay, because it's in Chinese now. Okay, I think this is end. That's I think one of lecture I delivered. So in some during for some international conference. Okay, that means okay. According to second law of thermodynamics, when we provide cooling, in fact, we generate heat. Okay, it's not cooling, but it's so it's mentioned. So the publication for the Nature Photonics. Yeah, according to second law of thermodynamics, air conditioning, in fact, is a heat generator. Okay. Thank you. Okay, thank you, students online. Bye-bye. Good night.